Conductance of electrolytic solutions. The electrical resistance of any object is directly proportional to its length. This is something you already know in case of wire. For example, in physics, you have a wire, metallic wire, and this wire's resistance will depend on its length. Greater the length, higher will be the resistance, or smaller the cross sectional area, higher will be the resistance. Means resistance is inversely proportional to cross sectional area of this wire. If you increase the cross sectional area, resistance will decrease. Okay, and resistance is proportional to length. If you increase the length, resistance will increase. So when we combine these two, we get resistance is proportional to L by A. L is in numerator, A is in denominator. So when we combine these two, resistance is proportional to L by A. When we remove this proportionality constant, we get R equals to rho L by A. This is something you might have done in physics, which is applicable to all metal wires, etc. Okay. Mehak, for that, everyone has to send the assignment number and question number and the test and the question number. And for test, basically not just the question number, the question itself. So this is for everyone. You need to send me if you have any confusion in any assignments. So assignment number and then question and test and the question itself, because in test you might have question number 1 as question number 4. Different students will have different numbers. So for test you have to send the question, for assignment you have to send the question number, everyone, so that I can collate and can prepare one class for that, and that will save time. Okay, we can do 3-4 more questions if you just send the details to me in advance. So here this rho is proportionality constant, which is known as resistivity. So there is difference. This is resistance. Rho is resistivity or specific resistance. So here also resistance will come into picture, but a specific term will be there. Resistivity or specific resistance. And these terms are confusing, so you need to pay attention here. SI unit is ohm meter, because rho will be equal to R A by L. From this, rho will be R A by L. R unit is ohm. A by L will be meter square by meter, that is meter. Ohm meter, unit of resistivity. The resistivity for a substance is its resistance when it's 1 meter long and 1 cubic square meter area is there. What you can say, this formula is R equals to rho L by A. Both of these will be equal. R will be equal to rho if L is 1 and A is 1. That is the definition of resistivity basically. So if you have conductor whose length is 1 meter and the cross sectional area is also 1 meter, means this area is also 1 meter square. Then in that case, its resistance will be equal to its resistivity. That's how we define resistivity. Resistivity is equal to the resistance of a material when its length is 1 meter and cross sectional area is also 1 meter square. Now area 1 meter square, it can be 1 by 1. It can be 0.5 meter by 2 meters. Even then cross sectional area will be 1 meter square. It does not necessarily mean that you have to have all depth dimensions as one. Only the length can be one, must be one. Area in any form should be 1 meter square. So that's what is written here. Definition of resistivity. Resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is also 1 meter square. So definition is given by this formula. The inverse of resistance is called conductance. Conductance is denoted by G and it is given by inverse of resistance 1 by R. So R we know rho L by A we have substituted here. 1 by rho has been given another name constant as kappa, Greek letter kappa. So if you remember R equals to rho L by A, you can write 1 by rho equals to 1 by R. R you moved here, rho you moved here, and L by A you moved on left hand side. So it will be A by L. 1 by rho is kappa, A by L. 1 by R is G. It means G equals to kappa A by L. Okay. So you might not memorize this formula. If you memorize, it's fine. You can get it from R equals to rho L by A. R is equal to rho L by A. R is 1 by G. Rho is 1 by kappa L by A. It means G is equal to kappa A by L. Okay. You just need to remember that G is inverse of R, kappa is inverse of rho, reciprocal of rho. SI unit of conductivity, Siemens per meter. What is conductivity? Kappa is conductivity. G is conductance. R is resistance. Rho is resistivity. Okay. Rho is also known as specific resistance. Kappa is also known as specific conductance. If it is only conductance, it is G. Only resistance, it is R. Conductivity, resistivity, these are the proportionality constants. Conductivity, resistivity, these are proportionality constants, kappa and rho. So from here, if you see the units of conductivity means kappa, kappa will be equal to G L by A. From here means its units will be Siemens. L by A means meter by meter square, that is per meter. Or you can say Siemens is conductance, conductance is ohm inverse, meter inverse. Okay. Or ohm inverse, meter inverse. Sometimes it is mentioned in per centimeter also, centimeter inverse. The definition again, the same thing, because you know G is equal to kappa A by L, and G will be equal to kappa if A is 1, L is 1 unit. So same definition here applies. Conductivity, that is kappa, is that conductance, that is G, when the substance is 1 meter long and its area of cross section is 1 meter square. Then both will be equal. It means when I talked about the resistance definition and conductance definition, if we have this arrangement 1 meter and this area is 1 meter square, in this case, R will be equal to rho and cup P will be equal to cup. This can be of any shape. The only requirement is length should be 1 meter. The area can be 1 square meter in any form. Earlier, only metals and their alloys at very low temperature. Here we are talking about superconductors. Okay? Only metals and their alloys at very low temperature, that is 0 to 15 Kelvin. 0 is absolute. 0 Kelvin is absolute zero. Temperature cannot be below this one. So these were known to behave as superconductors. But now a number of ceramic materials and mixed oxides are available which show superconductivity at temperature as high as 150 K. This is again negative temperature in degrees Celsius. 150 K is negative temperature. But much more than 0 to 15 Kelvin. Means at this temperature 150 K, we have few materials which offer zero resistance. Zero resistance. When electrolytes are dissolved in water, now we are moving to electrolytes from the concept of wires, materials. Now we are applying the same logic, same concepts in electrolytes. When electrolytes are dissolved in water, they furnish their own ions in the solution, hence its conductivity also increases. So conductivity of water will increase if we dissolve common salts. Okay? Sodium chloride, for example, if we dissolve, its conductivity will increase because ions, number of ions will increase, and hence the conductivity will increase. The conductance of electricity by ions present in the solution is called electrolytic or ionic conductance. Here also we will be talking about conductance, but we will call it ionic conductance because it is due to ion. However, going forward, you will see we will use only conductance term. We will not use ionic, even though we will be talking about electrolytic solutions. The conductivity of electrolytic solutions depends on many factors. The nature of the electrolyte added, for example, nature of NaCl, whether we are adding NaCl or we are adding KCl or we are adding something else, MgOH whole twice. Okay. Size of the ions, first nature of the electrolyte, size of the ions, nature of the solvent, whether we are adding in water or whether we are adding in alcohol, and its viscosity, concentration of the electrolyte, how much we are adding. So it will depend on how much we are adding, amount, and then temperature. It increases with increase of temperature. Conductivity of electrolytes increases with increase in temperature. These 5 points, just memorize. You will get objective question from here, and mostly the objective question is the conductivity of an electrolyte does not depend on. So three will be out of these five, and one will not be from these. So that will be the answer. Measurement of the conductivity of ionic solutions. How we measure. Measurement of the conductivity of ionic solutions is done in a conductivity cell. Conductivity cell is a designed cell in which we already know the area of the plates, the electrolyte being used, the temperature, the nature of the solvent, everything is known, right? So that's why we can calculate the conductivity. So two common arrangements are shown here of conductivity cell. So we know the area of these plates. Basically, what how we can visualize it? We can visualize that if the area is just this much, we can visualize that this much of the electrolyte behaves as the metallic conductor. So the current will flow between these two electrodes. Okay, it will depend on the area of the electrodes itself. Suppose we increase the area, then this whole electrolyte will conduct electricity from the ground. However, if area is reduced, the electrolytes will flow here only. So effectively, you can consider that this is the imaginary solution. You can say the substance, you can consider the metallic substance if you compare it, which you can consider the length of this and the area of this. So this length is known, length between these two electrodes is known. The area of these electrodes is known. Similarly, here in the arrangement is like this, or second one, the area is this much only, which is exposed to the electrolyte. This area is known. The distance between these two is known. So conductivity cell have area of cross section equal to A, which is known, and are separated by a distance L, which is known. Therefore, solution confined between these two electrodes is a column of length L and area cross section A. So we can consider here that it is column of length L and area of cross section A. And we can apply the same formula, R equals to rho L by A. Same formula which we used for metals, metallic substances, we can apply here. The quantity L by A is called the cell constant. So you need to memorize these things, what I am telling you. Till now, important points I have told you that 1 by R is conductance. 1 by rho is conductivity. Rho is resistivity, kappa is conductivity. G asterisk, or you call G star, is L by A, which is known as cell constant. And it is very important parameter because something will change, but cell constant will remain same. We will talk about it during the numericals. Cell constant of a particular cell will be always constant because length is same, area is same. Cell constant is equal to L by A. We are not changing length, we are not changing area. So cell constant will always remain same unless we deliberately change length or area, which will not happen normally. conductivity, resistivity. Okay. Now tell me, if I write G asterisk and G, it will be equal to what? Okay, they were very good. So Hina, very good. Arohi, no. Rita, good. Uh, Arohi, you need to basically, you are correct, but what do you call this? Ashi, yes, correct. You are telling me correct thing, Arohi, but yes, you will say kappa. You won't say 1 by rho. You say it will be equal to kappa. Why? Because G's asterisk, we know it is L by A, and G is 1 by R, right? And you know the formula, G equals to kappa A by L. A by L, if you bring on the left hand side, will be L by A, G equals to kappa, and L by A is G asterisk. So it will be equal to kappa. This will be used quite a few times, so you need to remember. Okay. Either you write G equals to kappa like this or like this, whatever way you need to remember. Or you write like this because R is 1 by G. Whether you write kappa by G or kappa R, same thing. So that's what is written here. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation kappa equals to cell constant divided by R, which we will be using in numericals also. Then molar conductivity. Molar conductivity and conductivity are different things. You need to understand it very clearly. When I say molar conductivity means I am talking about the conductivity when we have 1 mole of something. Okay. So molar conductivity denoted by lambda m. This is lambda, capital lambda, small lambda, lowercase lambda is like this. It is related to conductivity of the solution by the equation. Molar conductivity is given by kappa by C. And here common mistake, if you don't pay attention. C is concentration, that's fine, but unit of C is very much different here. C is not in mole per liter, rather it is in mole per cubic meter. Kappa is same, ohm inverse, meter inverse, or Siemens meter inverse. Okay. So if you write the definition, If you see the units here, this is per meter, or you write meter inverse, here write meter minus 3 bar. So when you combine these two, you get units of molar conductivity as Siemens meter square per mole. That's divided by Siemens meter inverse divided by mole meter per minus. These units are important. You need to remember Siemens meter square per mole. Because we are talking about molar conductivity, it will be when we have 1 mole of the substance. Okay. 1 mole of the substance. We are not talking about that we have the concentration mole per liter. No, in 1 cubic meter. Now the question, and it will check your knowledge whether you have got it or not. Resistance of a conductivity cell filled with zero point 0.1 mole per liter KCl solution is 100 ohm. R is given 100 ohm, zero point 0.1 mole per liter. If the resistance of the same cell when filled with 0.02 mole per liter KCl solution is 520, R1 is 100, R2 is 520 ohm. Calculate the conductivity and molar conductivity of 0.02 mole per liter KCl solution. Now, first, don't give me the answer. First, tell me which concept you will be using here. Which concept? For the first part, calculate the conductivity of the KCl solution. Molar conductivity we will talk about later. First, tell me for conductivity, which concept you will be using. Resistances are different. Yes, correct. I think just let me check who has given me correct answers. Yes, Preeta, yes, fine, but tell me which concept we need to use here. Which constant? Which is constant between these two? I have already told you this just few minutes back that it will remain constant. I told you. Yes, they will. You can make use of that. Okay. How? Cell constant will remain same. I talked about it few minutes back. So cell constant we will calculate first with the given amounts. So the given amounts, if you see here, conductivity of 0.1 mole per liter KCl solution is given here. So kappa 1 is given 1.29 Siemens per meter. Here kappa 2 is asked, this one. Okay. So the 0.1 mole per liter solution is of 100 ohm. 0.02 mole per liter is of 520 ohms. But these two are interrelated. Cell constant is conductivity into resistance. So what you can say, because this will remain constant and it is equal to kappa R, means kappa 1 R1 will be equal to kappa 2 R2. Both represent cell constant. So here you calculated cell constant. There are two ways. Either you first calculate the cell constant and then use it, or use kappa 1 R1 equals to kappa 2 R2. Same thing. You will get same answer. So we have converted it into 1.29 per centimeter. Then conductivity of 0.02 m KCl solution, it will be G naught by R. Kappa 2 will be G star will be kappa 2 R2. From here, kappa 2 equals to G star divided by R2. G will remain same, 129 per meter, divided by R2, 520, you get the answer. Whether you solve like this or you solve like this, kappa 2 R2 equals to kappa 1 R1. Kappa 2 you have to calculate, R2 is 520, kappa 1 will be, was given, it was 1.29 Siemens per meter, into R1 was 100. Means kappa 2 equals to 1.29 into 100, 129 divided by 520, which is same as you get here, means 0.248 Siemens per meter. Now Siemens per meter is SI unit, but normal practice is to use per centimeter. And the reason is, normally we electrolytic cells, we don't have, that much large that we can have meters there. Electrolytic cells are very small in dimensions, and hence units in per centimeter. In formula, units will be per meter, but answers normally are represented in per centimeter. Reason, the dimensions are not too large. I'm going back so that you can understand how to calculate the molar conductivity now. So in first case, remember we didn't make any use of these things because cell constant depends on the conductivity and resistance only. Conductivity multiplied by resistance gives you cell constant. Now we need to calculate molar conductivity. And molar conductivity formula, kappa by C. Molar conductivity, kappa by C, where C is mole per cubic meter. Okay. So you will convert the concentration. You have to calculate the molar conductivity of 0.02 mole per liter solution, KCl solution, not of 0.01 mole per liter KCl solution. Okay. So remember the question, a few students, if you are confused. We have this cell. Initially, we had a 0.1 mole per liter solution into it, and it offered 100 ohm resistance. Then we had taken in the same cell 0.02 mole per liter solution. Then it offered 520 ohm resistance. Okay. In both cases, this is the relationship here. The conductivity of 0.1 m, this one, is given 1.29 Siemens per meter. Here, kappa, we don't know. That is what is asked. We didn't require this thing here. We know the relationship between these two. Cell constant is kappa into R. Cell constant is equal to kappa into R. Out of these four, only one was unknown. We calculated that. Now for the second part, molar conductivity. Molar conductivity of 0.02 mole per liter. So now the cell is of 0.02 mole per liter. So we will convert this to mole per cubic meter, because the molar conductivity we have to calculate is kappa by C. Kappa we have calculated in the previous case. Okay, we have calculated. here for this one, 0.02. This C we will convert into mole per cubic meters. We'll substitute these values, we will get molar conductivity. So that's what we have done here. 0.02 mole per liter, we have converted it into mole per cubic meter. Yeah. 1 liter is equal to 10 to the power minus 3 cubic meter. Okay. So how will you convert it? Understand it. Concentration is 0.02 mole per liter. Liter inverse means in the denominator you have liter. This liter you have to convert into cubic meter. So 0.02 mole, 1 liter is equal to 10 to the power minus 3 cubic meter. You converted this 1 liter to cubic meter. So 1 liter is equal to 10 to the power minus 3 cubic. It means it will be 0.02 into 10 to the power 3. This when goes to numerator 10 to the power 3 mole per cubic meter. That is 20 mole per cubic meter. That's how we have converted this. Concentration C we got in mole per cubic meter, substituted the values. This is something we calculated in previous part. This one is concentration for the answer. Once we got the answer in meters, we converted it to centimeter. Even if you don't convert, this answer is correct. That is just a normal practice that you convert it to centimeter. Any confusion, let me know. Right, next question. The electrical resistance of a column of 0.05 mole per liter NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 power 3 ohms. Calculate the resistivity, conductivity, and molar conductivity. What is given? 5.55 into 10 to the power 3 ohms resistance. Concentration is given 0.05 mole per liter. Diameter is given, length is given, 50 centimeter. That is 0.5 meter. Area will be pi r square. Diameter is given 1 centimeter. If you are using meters, you need to convert it into meters and then the radius. So from here you will calculate the area. You have length, you have r. You need resistivity, means rho. You need conductivity, means kappa, and you need molar conductivity, lambda. R is equal to rho L by A. You know everything. Make sure that you use the same units. Here, R should be in meters. So diameter is 1 centimeter. Radius will be 0.5 centimeter. 0.5 centimeter, you have to convert it into meter. Okay. So it will actually be 3.14 into 0.005 whole meters, because you have to consider 0.5 meter is centimeter is equal to 0.005 meters. You will divide by 100. Substitute these values, you will get the answer. Conductivity, kappa, you know how these are interrelated. Yes, R equals to rho L by A, kappa is 1 by rho, correct. So how these are interrelated, you know, once you got the rho from here, Kappa is 1 by rho. You will get that answer. And then molar conductivity kappa by C. Remember, C you need to convert into mole per cubic meter. So C is given as 0.05 mole per liter. It will be 1000 into 0.05, that is 50 mole per cubic meter. Either you divide by 10 to the power minus 3 or multiply by 1000. It is same thing. So substitute these values, whatever kappa you have got here and whatever C is there. Substitute these values, you will get the answer. From R equals to rho L by A, you will get rho. The moment you got rho, you will apply kappa equals to 1 by rho. You will get conductivity. From this conductivity and the concentration in mole per cubic meter, you will get the answer. So either you write kappa by C or you write kappa 1000 by C, then you can use this, okay, in centimeter per liter. So sometimes this formula is also used, and you need to be cautious that if you are using this formula here, you will be writing C in mole per liter. You are not changing the dimensions here. But the unit of molar conductivity will come into centimeter cube per liter. So that is something you need to be cautious. Otherwise, if you are confused or you want to avoid confusion, use lambda m equals to kappa by C, where kappa is 1 by rho and this one is in mole per cubic. Accordingly, here the units will be meter square mole inverse. Instead of centimeter square mole inverse, units will be in SI system. With practice, once you have done, around 5-10 questions, after that you will find that you can use both the formulas without any problem. If this is used, units will be centimeter cube per liter, or you can say the unit will be Siemens centimeter square per mole. Now, variation of conductivity and molar conductivity with concentration. From here, you normally get question, the conceptual type question. Why this happens, why this will be more than the other one, those type of questions, or whether something will increase or decrease, the conductivity will increase, molar conductivity will increase with dilution, or up to what extent. Those type of questions will be from here. Concentration will change conductivity and molar conductivity. Conductivity always decreases with a decrease in concentration. Means conductivity is always proportional to concentration. For weak and strong electrolytes, conductivity always decreases with decrease in concentration, means it will increase with increase in concentration. For weak and strong electrolytes, this can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The important point which you need to understand here, so that you can understand the molar conductivity also, the important point here is per unit volume. Because the number of total ions will increase. The number of total ions on dilution will increase. Here we are saying number of ions per unit volume will decrease. Understand what I am saying? Suppose you have a beaker and you have some electrolyte, okay, dissolved in some solution. So this is electrolytic solution. Electrolyte is already present, and this is strong, very strong electrolyte. So you have NaCl dissolved in water. Now suppose you add some water in dilution. Now you added water. Now when you added water, the number of sodium ion and chloride ion will increase. In dilute solutions, NaCl will get ionized more. So when you add water, for example, water is solvent, then more sodium and chloride ions will be there in the solution. Ionization will increase, but ions per unit volume will decrease. Means if this was the unit volume, this is the unit volume, this is the unit volume, this is the unit volume. So whatever number of ions were here earlier, number of ions per unit volume will be less. Will decrease. Total number of ions will be more than the previous case, but per unit volume, it will be less. That's why conductivity will decrease on dilution. Means decrease in concentration. As conductance is given by kappa A by L, the conductivity of a solution at any given concentration is the conductance of 1 unit volume of the solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. Here this is slightly, you have to understand what I am saying, because nowhere in this formula volume is mentioned, but still I am saying volume here, 1 unit volume. Why I am saying 1 unit volume? Because if I have this arrangement, for this arrangement I said that you will have unit length and unit area. This length is 1, this area is 1 meter square. Say 1 meter, 1 meter square. Then what will be volume of this one? Length into area, that is 1 unit, 1 cubic meter, 1 unit. So that's why I am saying unit volume here. The conductivity of a solution at any given concentration is the conductance, is the conductance, conductivity will be equal to conductance when area is 1, length is 1. And when area and length are unit, the volume will also be 1 unit. So that's why it is written here. The conductivity of the solution at any given concentration is conductance of 1 unit volume of the solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. We are saying the same thing what we have said earlier, but instead of just saying unit cross sectional area and unit length, now we are moving towards unit volume, because there will be 1 unit volume if area is 1 unit and length is 1 unit. And then whatever conductance is there, that will be conductivity. Molar conductivity. Molar conductivity of a solution at a given concentration is the conductance of the volume V of the solution containing exactly 1 mole of electrolyte kept between two electrodes with area of cross section A and distance of unit length. Ashi, platinum electrodes are used so that platinum is the highly passive. It does not react. So that's why platinum electrodes are used, so that they just conduct electricity and do not react. So in this case, molar conductivity, you need to understand 2 points, just 2 points, that it will always have 1 mole of electrolyte. Volume will be something V. Volume will not be unit. Volume will not be unit. So when we say here unit length, so these are the conditions you have to remember. Okay, distance unit length, some area. Now, if distance is unit length and area is A, then volume will be area into length. That is, volume will be equal to area because length is 1. So volume will be equal to area. I'm talking about absolute value, not the units. Units will be different, but their values will be same. Since L is equal to 1, A will be V by L, that is V by 1, that is V. Volume containing 1 mole of electrolyte. Hence, molar conductivity is equal to kappa into V. Instead of saying kappa into A by L, we substitute these values. We know that lambda is equal to lambda m equals to kappa A by L. But here we will say lambda m equals to kappa A is equal to V, L is equal to 1, means kappa V. So in terms of volume also we can use lambda m is equal to kappa V. Hence, molar conductivity increases with the decrease in concentration. Can you tell me why? Molar conductivity increases with the decrease in concentration. Why? Who will tell me? You are just using the formula I have written. Lambda m equals to kappa V. No, not inversely. When you are decreasing the concentration means you are increasing the volume. You are adding more solvent. Decrease in concentration means adding solvent. When you add water into it, remember it will again remain 1 mole. Electrolyte will remain 1 mole even if you dilute. Even if you add solvent, the electrolyte concentration is changing, but amount is not changing. If it was 1 mole, it will remain 1 mole. Only concentration will change. Volume will increase if you add more water. So because volume will increase on dilution, lambda m will increase. So molar conductivity will increase on dilution. It's written here because the total volume V of solution containing 1 mole of electrolyte also increases. And this is the difference. From here, you will get a question that why conductivity decreases with dilution, but molar conductivity increases with dilution. The reason for the conductivity was that although on dilution the number of ions increases, but the number of ions per unit volume decreases. And that is the conductivity, that is mole per liter. So here for conductivity, we said conductivity concentration here is mole per liter. Okay. So it is related to conductivity per liter. conductivity in 1 liter only. But molar conductivity is conductivity of 1 mole. Whether the volume is 1 liter, whether the volume is 10 liter, whether it is 20 liter, does not matter. Whatever volume has 1 mole, that we have to consider in case of molar conductivity. So remember, again, I am comparing both. When I am saying conductivity and molar conductivity, when I am saying conductivity, this is per unit volume. On dilution, number of ions per unit volume decreases. That's why conductivity decreases. On dilution, although ionization increases, yet conductivity decreases because ions per unit volume are less than previous case. Molar conductivity, this is conductivity of 1 mole of a solution. Conductivity of a solution, electrolytic solution containing 1 mole of the electrolyte. Okay, whatever the volume is, okay, irrespective of volume. Irrespective of volume does not mean that it does not depend on volume, right? Means volume might be anything. Okay, volume will change accordingly. Now here, on dilution, number of ions will increase in 1 mole, hence conductivity, molar conductivity will increase, because this is not per unit volume, this is of whole 1 mole, whatever amount we have. Greater number of ions, greater will be the conductivity, greater is the molar conductivity. Very common question appears from it. Yes, Dev, as volume increases, so by formula you can say this one, as volume increases on dilution, molar conductivity will increase. Limiting molar conductivity, this comes into picture because it's not that if you keep on increasing the uh, solvent, keep on increasing the dilution, molar conductivity will keep on increasing, because if you see this formula, if you make volume infinity, then it will be very good for us. We will get infinite molar conductivity, very good molar conductivity. Okay. Means conductivity, if infinity means resistivity is zero. But it is not possible. There is certain limit up to which the conductivity will increase. And there is reason for that. That is called limiting molar conductivity, lambda m naught. So when concentration approaches zero, means we have diluted the electrolyte up to a large extent. The molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda m naught. It does not increase beyond lambda m naught. This is the maximum conductivity it can achieve. So the variation in lambda m with concentration is different for strong and weak electrolyte. This is something I'm talking about lambda m, not limiting molar conductivity. I'll come back to that. Okay. So for example, I'm taking acetic acid. Acetic acid is weak acid, weak electrolyte. So for weak electrolyte, the graph is given, and this graph sometimes, you may be asked to draw. For that, you must remember that on the x-axis, you have taken concentration root. square root of concentration. It is not concentration, a square root of concentration. On y-axis in this graph, it is molar conductivity. So if you see for very weak electrolyte, molar conductivity, if we are talking about, this is the graph, blue colored graph. This one means if we decrease the concentration, the molar conductivity will increase. If we decrease the concentration, say here, the molar conductivity is this much. And if we decrease the concentration here, the molar conductivity is this much. And if we further decrease the concentration, molar conductivity is this much for weak electrolytes. Weak electrolytes, molar conductivity graph, you need to remember. This will be the graph. But beyond certain dilution, the molar conductivity will not increase further. Can anyone tell me the reason why beyond certain dilution, the molar conductivity will not increase? What might be the reason? If we see this formula, from this formula, it seems that if V is infinity, we keep on increasing, lambda m will keep on increasing. But why after certain dilution, it is not possible? Answer is not tough. Answer is easy. Okay, no answer received. Okay, the reason is that up to certain, when we add the solvent, up to certain dilution, the ionization can increase. But at certain dilution, the whole of the entire electrolyte gets ionized. So there is no further unionized electrolyte after some time. After certain dilution, the ionization stops because you don't have the electrolyte which can get ionized. You have all the ions which could be maximum possible there. So that's why ionization is not increased, the conductivity does not increase. I hope it is clear. Ashi, what I am saying that suppose you have certain electrolyte, okay, and say it is Mx and it gets ionized into ions. So initially, if it is C and it gets ionized, C alpha, C alpha, C alpha will be here. Okay. And ionization will keep on increasing when you dilute it. But after a certain time, if it gets ionized, there is certain limit it can get ionized, alpha. Okay. So depending on this alpha, say it can get ionized 60%, say. Okay. So maximum ionization is 60% means it will be C minus 0.6 C. And here 0.6 C and 0.6 C will be produced. After that, even if you add water into it, the ionization cannot increase, will not increase because the ionization constant is fixed. Degree of ionization alpha is fixed. So it cannot get ionized further even if you add more water. That's why molar conductivity will not increase. after certain dilution. This graph, I would suggest that you need to draw at least 3-4 times draw so that you remember. So blue graph is for weak electrolyte. But for a strong electrolyte, that is KCl, for example, the graph is a straight line. Okay. So for a strong electrolyte, that is KCl, for example, the molar conductivity increases slowly with dilution and can be represented by this equation. Now, if you see this equation is of the form of lambda m equals to minus AC to the power 1 by 2 plus lambda m naught. I have moved lambda m naught here and this one here. Okay. Now, if we compare it with y equals to mx plus c, it means on x-axis, I have square root of c. On y-axis, I have molar conductivity. The slope is minus a. And this is a straight line. The intersection on y-axis is limiting molar conductivity. This is c, y-intercept. And that's what you see here in this diagram. The slope is negative. This is of this shape. That's why. And where it will touch the y-axis, this will give you lambda m naught. Slope is minus a. X-axis is square root of c. Y-axis is molar conductivity lambda m. So for this straight line in the graph and a strong electrolyte, you need to remember the graph as well as the equation here. Lambda m equals to lambda m naught minus a c to the power 1 by 2. Direct numericals will be there based on this particular equation. Molar conductivity of KCl solution at different concentrations at room temperature is given here. So C is given, obviously you will calculate C square root and based on that lambda m values. Show that a plot between lambda m and C square root is a straight line. So what you need to do, you need to convert this graph into the same thing. This will remain same, but you need to have a square root of these. From that, you will draw the graph. And when you draw the graph, that graph will come out to be a straight line. And these points, when you join, these points will intercept somewhere at y-axis. This is molar conductivity on x-axis. You have square root of c. Where it intercepts the y-axis, that will be lambda m naught. You have been asked to calculate lambda m naught, you will get from the graph in this case. And A will be slope. Okay. How will you calculate slope? Slope you will calculate, suppose you get some values of C half. Okay. Say you get X, Y, Z, etc. Slope you will get this minus this divided by this minus this. Means like this. These two values and these two values. I hope you have done that in maths. Difference here. Okay. Say this one is 148.61. This one is 147.09. So their difference divided by these two differences. Suppose this is W, X, so this one is W, this one is X, for example. The slope will be y2 minus y1, that is 148.61 minus 147.09 divided by x minus w, sorry, w minus x, because 148 corresponds to w, so that's why w first. And because w is less than x, it will come out to be negative. And you know that slope of this line, which is of this shape, is negative. Yes, Dev. Y2 minus y1 equals to x2 minus x1. That's what you will use for slope. So you need to find from the graph. However, the questions based on graphs in last few years have been very, very rare. Very, very rare. And because this year again, due to Corona, there is very, very rare chance that you will get question based on graph. But still you need to know. So we take the square roots of the concentration, we get these values. Now we can draw the graph with these values. We join those points, we get a straight line where it intersects the y-axis, that will be lambda m naught. It intersects here. This point will be 150. 150 will be the lambda m naught. A slope. Slope will be any two values, this and this difference and these differences. Basically, you need to consider these, whether you consider this one, and this one, you can get the answer. Delta y slope is always delta y divided by delta. From here, you will get the slope. It will come out to be negative in this particular.